and make sure you are energized and well tomorrow. And do use tomorrow afternoon to study for the exam on Sunday. That one you should. Yeah. Okay, very good. So it's a pleasure to have Ricardo close off the school with the last standard model lecture.
Thank you, Pedro. So now we resume from where we left off last time, right? So I hope I have convinced you that once you introduce a scalar, right, and that scalar develops a vacuum expectation value, right, spontaneous symmetry breaking occurs in the standard model, right? And for that specific breaking pattern, what happens is that you mix the SU2 and the U1 gauge bosons, right? And you mix them in a very specific way, right? You can substitute, that was one of the exercises, right? You can substitute that vacuum expectation value in the covariant derivative for the Higgs and get this result right here, where you have 3 massive gauge bosons, and since you had 4 at the start, that means that there's one that is left massless, right? Which we'll try to identify with the photon today, right? Of course, that's not the most convenient basis to do that, right? Because we also want these guys to be eigenstates of interaction. And in order to do that, we do a little change of variables, right? We define these 2 fields here, which are combinations of those that you had there, right? And another one, which is the massless combination, right? So if you go back there with this combination, you see there's no quadratic term for this A mu. You only get quadratic terms for the W's and the Z's, and these are the masses, right? And the masses in this case are predicted by the symmetry breaking pattern, right? These are numbers that arise once you substitute these in here, right? And this is what they are. So the mass of the W, the mass of the Z are here, and they have this common pattern, right? With the simplest example I gave you for U1 spontaneous symmetry breaking, where the masses obtained by the gauge boson there, right, are proportional to the VEV, the vacuum expectation value of the scalar, and the coupling of that gauge boson with the scalar, right? So it will be proportional to these 2 things, right? Either of them goes to zero, it becomes massless again, right? Which is equivalent of saying that if that coupling goes to 0, it means that the scalar didn't transform under the symmetry, so it was not broken anymore, right? Another thing that I didn't mention last time, but is an important one, is that this ratio does not depend on the VEV, you see? And that's a very, very important parameter. It's a very important prediction for the standard model, is this ratio of the W mass with the Z mass, because it depends a lot on the symmetry breaking pattern. If you change it, this ratio changes, and that's a very well precise measured quantity, right? So I'll put it in better terms in a minute or two, right? So now what we want to see is doing this substitution, right? Changing from these gauge bosons to these ones in blue, right? How do the interaction with the fermions and the scalars look, right? So I'm going back now to the covariant derivatives, right? Maybe, yeah. Today I will use the blackboard very little, mostly for questions, I guess. So you see, any particle, scalar or fermion, that transforms under SU2 times U1 will get this covariant derivative, right? That's how it interacts with the W's and the B, right? It's equivalent to this minimal coupling that you do sometimes in electromagnetism, right? Now, if I do that substitution, right, I replace W1, W2, W3, and B here by these 3 states as defined here, right? What I get is that this derivative now becomes this thing, right? So in the interaction with the W's is given by this combination. Remember that T1 and T2 here are nothing but the Pauli matrix is divided by 2. Right? So the interaction with the W's happens with this the first Pauli matrix and the second one combined in this way. But the interaction with the Z and with this guy that I want to identify with the photon happens with this more complicated matrix structure, right? But you see, here I have T3, which is the third Pauli matrix, which is diagonal, right? And the identity. In here I have a 2x2 identity, right? It's just numbers. Same here. So see, these two interactions are diagonal, and this one is not. So that's the first consequence. It's a very important consequence to the standard model. This is not the proof of it. You have to do a little more work, but it's already a hint in that direction, which is, remember, this is the isospin group, right? Every left-handed particle in the model come in a doublet, right? We have an up part and a down part. It can be the up quark, down quark, charm strange, a neutrino and an electron, right? Once you interact with the W, you face that T plus or T minus matrix, which will rotate here. That means when you interact with the W, you change from up to down or down to up, right? So emitting a W can transform an electron in a neutrino, for instance. But interacting with the Z or the photon does not do that. It's diagonal, right? If you're up, you continue to be up. If you're down, you continue to be down, right? There's a more general theorem that shows that in the standard model, this is true to even at loop order, right? That you have no flavor changing neutral current, right? So you do not, at least at 3 level, you do not have flavor changing neutral currents, right? In order to change flavor and to go from up to down, you have to emit charged particles, which are the W's. So that's one important constraint that you get there, right? And now I can rewrite all the covariant derivatives to reflect that. Another thing that, well, I'll talk about that in a second. Right? So these are the covariant derivatives for the fermions. Right? I have essentially 4 types of fermions in my theory: left-handed quarks, right-handed quarks, left-handed leptons, and right-handed leptons. Right? And the covariant derivative looks different because they have different group transformations. Right? So the most complicated one is the left-handed quark, right? It transforms under SU2, under U1, and under SU3 color, right? And these are the 3 parts that you see here. This is the gluon, right? A right-handed quark does not have SU2, so it's equivalent to taking this T here setting to 0, right? The left-handed leptons now, the leptons have no color, so the gluon goes away. And only the left-handed leptons have SU2. So the right-handed leptons only have really the U1 interaction. Of course, once you mix these guys, it gets more complicated, right? So now, let's look specifically, right? We want to identify this guy with a photon. So let's look specifically at this interaction, right? It suffices to look at the covariant derivative, right? Because that's where the interaction appears. Now we have 2 parts here. One that is really intrinsic to the theory, right? This will be the same for every fermion that I apply. It's just a number, a combination of G and G prime, which are the 2 gauge couplings for SU2 and U1, right? And there is a part which these operators act on the fermion and will depend on the quantum numbers of the fermion, right? So I clearly have these 2 different quantities, and here I'm just repeating which matrices are acting on this guy. Remember, this guy is a 2-component isospin object, right? And the thing is, I can just take this guy and name E by accident. Right? It's a number, right? I'll have to fit that number to experiment, but it is a number which I decide to name E. What happens with these guys? It can act on basically 3 different objects, right? It could be on a pure up state, right? And you see this is an eigenvalue of eigenvector of this T3 with eigenvalue plus 1/2. Because this is isospin, right? This is a spin up and this is the spin up down, essentially, right? Same thing. I'm just acting with the third polymetrics there. Right? And same thing here, right? The pure down state will have a minus half here. Y is just multiply the identity, right? And I can even think of singlets as having 0 isospin, right? They are singlets, they do not transform. Essentially, you don't have this part of the covariant derivative there. T3 is not even there, but that's the same as having T3, the eigenvalue of T3 equal to 0, right? They are singlets. So this number here for the right-handed guys, for the singlets, will be just Y. And now I can think of it as a electromagnetic interaction, as long as I identify that some, now T3 is understood as the eigenvalue of T3 on that state, right? As the charge, right? I just have to choose these hypercharge. Then I have shown you the choice for hypercharge that we do, right? So that these charges reflect the properties of the standard model. And here is the table, right? You can see that for every state, right, T3 plus Y will give the observed charge of the particle, right? And of course, the hypercharge needs to be the same for both partners in a doublet, right? So it was not obvious that you could find just one value of Y that would solve for these two charges, right? But it works, and it shows that you have the right symmetry breaking pattern, right? The only strange thing here is really the right-handed neutrino, right? I'm including these in a talk about the standard model, but it's really not in the standard model. And you see the reason here, right? This guy has no SU2 interactions. He has no hypercharge interactions. He has no electric interactions. He has no color, right? That's a philosophical particle, right? Not a physical one. If it doesn't interact with anything, right, it's like the tree that falls in the forest and nobody sees it, right? So this is why the right-handed neutrino is not in the standard model. Huh? But it could be to play just one role, and I'll get to that later, right? So that is where you can justify the choices for these hypercharges. There's another justification that has to do with anomaly cancellation, but we won't have the time to get to that, right? The same numbers work there, luckily, right? And always good, and that's how electromagnetism arises from these two groups, you see? As you break, you get not only massless gauge boson, which we can identify with the photon, but also you can find all the appropriate charges combining the charges from the two broken groups. Right? So, what now, right? This is just another way of putting it, right? So we now exchanging these, and now I identify that number with the electric charge, right? I can also do the same, right? I'm exchanging G and G prime for E. But these are two variables, so I cannot exchange just for one. The choice people usually make is to define this weak angle, which is defined in this way. We call it an angle because you can see if you sum the squares there, you get 1, right? And then express everything in the standard model, either in terms of G and G prime, or in terms of electric charge, and here understood as the constant, right? Not the charge of the electron. The charge of the electron is minus this number, right? And this weak angle, right? And if I rewrite the coupling of the Z and the photon in terms of these two variables, right? This is sine of theta square, sine, cosine, right? I have this kind of interaction. So you see how the Z interacts with fermions, how the photon interacts, right? And you have QED right there. And now we can also, as I said, right, this ratio between these two masses, right, is a very important quantity for the standard model, right? And you can also express this instead of G and G prime in terms of these variables. In fact, this is 1 over the cosine of the weak angle, right? So you can put that straight away in this form. and then define these parameters, called the whole parameter of the standard model, is measured to less than 1 part in 1,000 nowadays, right? And it's a pain in the neck of everyone that tries to build beyond standard model physics, right? Because anything, almost anything that you do to the symmetry breaking pattern will contribute to the mass of the W and the mass of the Z in a different way than exactly this one, and it deviates. You contribute to this rho, right? There's even a whole area of beyond standard model physics that focus only on models with custodial symmetry that preserve this number, right? You change the model without changing this rho parameter. It's not easy, right? It's very easy to break this relation. Okay. So, what about the fermion masses, right? I have told you that because you can rewrite psi bar, psi s, psi bar L, psi right, plus psi bar right, psi left, right? That masses are forbidden in this model, right? Right and left-handed part transforms differently. So these are not invariant, right? So masses are forbidden. Well, that's what is written up there. So essentially now I'm writing all the kinetic terms for all the fermions here. This sum is over all those 12 fermions that you had on the table, right? Everyone has a kinetic term, but then you just write this kinetic term in this way. Both of these are invariant under the SU2U1, but you have no masses, right? What can you do? Again, the Higgs comes to the rescue, right? You can write something like that. Why? Right? Because this guy is a doublet of SU2, but so is the Higgs, right? The Higgs is also a doublet of SU2, right? So when this left-handed guy transforms like this is the SU2 transformation. You get a minus here because it's the dagger of psi that is there, right? The Higgs transforms like that, okay? So it's invariant under SU2. And all three guys here also transform under U1. So you get a factor that is proportional to this. This is the parameter, right? The small transformation of U1. You get these three contributions, one from the left guy, one from the right guy, and one from the Higgs. And this will be invariant as long as the three hypercharge sum so to give a 0, right? And since the hypercharge of the Higgs was chosen to be a 1/2 to satisfy this, right? This is the condition between these two guys. But that's not the only way you can do this. There's one more way, right? Which is this one. You can also define this Higgs tilde there, right? Which is nothing but this, right? I'm just taking the complex conjugate of the Higgs and multiplying by a matrix, which is this one. I'm just flipping the up part with the down part of the Higgs, right? So I'm not introducing a new field, right? It's just a term. I could just write this in the Lagrangian in this way if I wanted. So I'm not introducing a new field. It's just a complex conjugate. But it's convenient to call this H tilde, right? There's no new degrees of freedom. It's the same 4 that I had before. H, phi 3, phi 1, and phi 2, right? It's the same thing. But in this case, and that's an exercise you can show, right? That this guy, as this, remember, this transformation goes through sigma 2. In fact, I think, no, it's right. As this transformation goes through this matrix in the middle here, it keeps its sign, right? But since I have H star there, the hypercharge occurs with the opposite charge, opposite sign, right? So for this term, the condition you have to satisfy is this one. Remember the first one, the difference between the left and right-handed hypercharges needed to be 1/2, and for this one, the difference needs to be minus 1/2. Right? So I have these two kinds of terms that I can use, right? And one of them will be allowed or the other depending on the hypercharges of these two guys, right? The left-handed part and the right-handed part of the fermion. Right? So I can go back to that table, right, and take a look. So I can take the up left here, compare with the up right, down left with down right, neutrino with neutrino right, etc. Right? and subtracts the hypercharge from the left part from the hypercharge on the right part, and that's what I get. So you'll see, for the up type guys, which is the U and the neutrino, it satisfies one of the conditions. For the down type guys, which is the down and the leptons, right? The electron, the muon, and the tau, right? It satisfies the other condition. So in the end, the Lagrangian looks like that, right? I have still to sum over these three families, right? The three generations of the standard model. But I'll have coupling with H for the downright, and here is something wrong. I think it should be the electron here and the neutrino here, right? I wrote wrong. Right? But I'll have a coupling with the H in two cases and a couple with H tilde in the two other cases, right? Depending on the right-handed part here being down. So for down type guys, which is these and these, should be H. So here should be H, right? And for the up type guys should be H tilde. Right? There's a wrong tilde in the wrong place there. Right? Again, I put the neutrino in pink for a very concrete reason, right? That right-handed neutrino that is there has no interactions, no gauge interactions. But this would be an interaction for him, right? That would be a solution to the neutrino mass. Right? I'll show how this becomes a mass in a second, if that's your question. Not straight out, no. It's too light. Maybe at the end I'll talk a little bit about dark matter, and you can ask the question again. Neutrinos would be candidates for dark matter based on their charge and other properties, but they are too light. So that causes a problem for cosmology. So now, how does that become a mass, right? This is just a coupling, right? What I'm drawing there is something like I have a left-handed fermion, a Higgs is still a doublet, right? Here I'm still talking about the thing before symmetry breaking. In here, I have phi 1, phi 2, you know, H and phi 3, right? So it's still a complicated thing, and the right-handed part, this is an interaction term in our Lagrangian. Right? How does that become a mass? Right? Now I have to substitute, right? Again, I take the Higgs. I'm forgetting about phi 1, phi 2, and phi 3 because they will generate complicated interactions and will mix with the W and the Z to give them mass. Right? But I'm keeping only the part of the Higgs that matters here. So the VEV, which is just a number, 246 GeV, and this guy, which is a field, is a real scalar field. And let me plug that in here. Let's take just this first piece, because the same happens everywhere. Right? So for this first piece, I'll have two parts, right? I'll have this one, which is just up, left, down, right, multiplying these, and I can now take this product. There'll be a part where these guys, of course, the up part goes away, right, because it multiplies this 0. You can see how, for instance, here, the V plus H will be on the top, because H tilde has V plus H in the top. So these terms, instead of choosing the down part of the left-handed, they will choose the up part, right? Which will combine with the up part here. But for this one, right, once you do this product, you get these two terms. And now it's clear what's happening, right? This is just, I'm using down to represent it, but this is just psi bar psi, right? For the down type, left-handed guy or right-handed guy, right? And I also, by the way, have the complex conjugate of all of these, right? Because the Lagrangian must be Hermitian. And then this is a mass term, right? Now, this coefficient in front of this psi bar psi is the mass for this fermion. But also, I get an interaction where I have fermion, Higgs, and now this Higgs is really just a scalar field which has a mass. We'll see, right? We know it must have a mass because we took a look at spontaneous symmetry breaking at the start. This is the guy that is not a Goldstone boson, so it must have a mass. We'll calculate it soon. Right? But now you have these interactions, which are Yukawa interactions. They are exactly the same as the one I mentioned at the start, right? Just like protons and neutrons interacting with a scalar, right? But the striking thing here is that they are not independent. You see the same number, which is this Yukawa coupling that I put here. This is a number. Is the strength of this interaction, right? Is controlling both the mass of the particle and how strong is the chance of it emitting a Higgs. You can think of that as in this way, right? If I turn this arrow to the future, this is the strength, right? The chance, or the square root of the chance of emitting a Higgs. And that's a prediction. Again, that's a very important prediction of the standard model, that the masses of all fermions should be proportional to how strong they interact with the Higgs. Right? This is not trivial. In a theory where these guys were not chiral states in terms of the interaction, if you didn't violate parity, then I could just put a mass term for them, and that mass would be another free parameter in my theory. It would have nothing to do with this coupling. In this case, they must be the same, right? And that's what I'm showing here. So the mass of the fermion is this, right? The strength of the interaction is the Yukawa over square root of 2. If I use this equation here, I can write also the interaction in terms of the mass of the fermion divided by the VEV, right? So see if the mass goes to 0, the interaction with the Higgs also goes to 0. And this is the experiment, right? This is a paper from Atlas from 2022, right? What you have in here is the mass of the particle, and here is the mass over the VEV, you see? Right here, exactly this quantity. This kappa that they put in front is kind of a fudge factor to adjust for loop corrections and all of that. You can treat kappa equal 1 for 3-level calculations, or fix kappa by one of the measurements and use the same kappa for everyone else. That's what they're saying here, right? You use the top to find out what should be the value of kappa for correction, for loop effects and all that, and you apply the same kappa everywhere. And you see the standard model prediction is the red line, right? And we have tested this for the top, for the bottom, for the tau, for the muon. Anyone suspects why we didn't test for the other ones? For instance, the charm, now I have a maximum value, right? This goes down to 0, right? I only have the maximum value for the charm. Anyone suspects why these guys are untested yet? I heard something, but I didn't understand. Yeah, they are too light, and the consequence is that the coupling is too small, right? So the lightest the particle, the smallest the coupling, harder it is to produce the event that you need. Essentially what you need is to find these, right? You have a very complicated event with a lot of particles, and at some point someone emits a Higgs. That's a direct measurement of the Yukawa coupling. Indirect measurements we have. You measure the mass of the particles, you calculate the Yukawa coupling. But that's not, that depends on your model. On the standard model, those two are related. But if you want to test your model, you must test the mass, measure the mass separately from the coupling, right? And that's the measurement they are doing there. By the way, in the same plot, they also tested the prediction for the mass of the W and the Z, right? That's based on G, G prime, and the VEV, right? These are all untested. The charm is underway. I think they have hope of actually measuring the Yukawa of the charm is still in the high luminosity regime for the LHC. The other are hopeless, right? You would need way more luminosity to even get close to measuring couplings that are much smaller than 10 to the 4, minus 4, right? They are just too small, and you need too much statistics. You never get that much in the LHC, right? So that part will remain untested for the foreseeable future. Well, now, these guys, who knows, right? Nobody even knows exactly how they get a mass. In principle, they could get a mass by exactly the same mechanism. Nothing says they can't. But then the coupling would be of order 10 to the minus 12. Right? We have sort of an idea what the mass of the neutrinos should be. We don't know the masses exactly, but we know the splittings in the overall scale. Right? And that tells me 10 to the minus 12, so you see it's if they are really getting masses through this same mechanism, we won't see right-handed neutrinos at all, but that doesn't mean they don't exist. They are just impossible to see with our technology today, right? Unless someone comes up with something really creative. But the coupling is really stupidly small. Right? Now, the Higgs sector, right? I already told you about the gauge bosons, the fermions. Now, what about the Higgs itself, right? There is this leftover scalar field. I can go back to the potential we had at the start, right, which is written like that, and do the same substitution. Just put the VAV and the real part of this field and write these Lagrangian. This is just substituting here and taking these products there. I get these Lagrangian, right? So you see, in this case, I have a mass for the Higgs, which is given by this part, right, is here. So again, the mass of the Higgs depends on the VAV, and on this new parameter, this lambda, which almost didn't show anywhere so far, right? I can get the VAV without measuring lambda, because I can measure the VAV straight from the masses of the W's and the Z's. And now, lambda is a new parameter. The only way we ever got information about lambda was once we observed the Higgs. We know the mass of the Higgs, right? It's 125 GeV. So we can calculate lambda. But this is the same case as the Yukawa couplings. In this model, the mass of the Higgs is given by the square root of lambda. But if you want to test the model, you have to measure lambda independently from the mass measurement to test if this relation is true. And this is another untested hypothesis of the standard model, right? These two interactions will generate a triple Higgs interaction and a 4 Higgs interaction, right? These are too hard to produce. Essentially, what you need to do is to get some event, and there are many ways of doing that. The simplest way would be this one. It's not the most efficient way. And then a Higgs produces 2 Higgses, and you try to measure that. This is double Higgs production. So far, we didn't do it. Right? We have an upper limit, still consistent with the standard model, but just no, not enough statistics. There's some hope that if you're just a little bit luck with the background, we can measure that in the high luminosity LHC, but as far as I know, this is hopeless. So another thing, right? This is measuring directly the potential for the Higgs, which is a very important parameter in the model, right? Fixes everything, but this we won't be able to know for sure in the LHC, because this is even harder, right? You would have to produce 4 Higgses or find some way to have Higgs scattering. Say these are 2 tops and you look for events like that. Those are all very low cross-section, right? So they get buried in the background. They are 1 event in a million, sometimes even less. And so they are all very hard to do with the luminosities we have today, right? So these are also untested predictions of the standard model. Let me just see if I forget anything before we move on. So maybe if you have questions about the standard model, this is the moment. Because then finally I'll go to the title of this course. Yeah. That it all depends on the details of the project, right? So the one that the CERN is pushing for, or some people in CERN are pushing for, is called FCC, which is a stupid name. It's Future Circular Collider, right? You shouldn't name something that you hope to build Future Circular Collider, right? It's almost like they have no hope of ever having it, right? But anyway, it would be 100. The LHC is 14 TeV, right? And in the same way that the LHC was built on top of LEP, so LEP was a previous generation accelerator, is now a pre-acceleration structure for the LHC. The LHC would then be a pre-acceleration for something even bigger, which will go to 100 TeV. When you increase the energy, you make a little bit easier to produce heavier particles. So you also have direct increases in luminosity, but you also have, more importantly, you have an increase in effective luminosity, how many of these particular events you can produce, right? So, and there's two proposals for that. One which is building a hadronic collider, and another one, a leptonic collider. And if you're doing that with electron-positron, then you can choose the energy and focus exactly, for instance, in when you have twice the mass of the Higgs to maximize the number of events you produce there. So, but this is 2050, if at all, right? Not before that, right? I can show you straight out all of them. Let me. This is so. This is the full Lagrangian, right? So this part 2 that you see there, part 2, right? This block 2 that goes up to here is what comes when you substitute the Higgs in that part of the Lagrangian that gives the masses of the W's and the Z's. If you remember my slide, I show this part. I show the Z square, which is here. And then I had 3 dots that said very complicated. This is the rest, right? So the Higgs in this notation is this big H here. So all you have to do is look for one that has HZ. Let me find one. So there's H4 here. These are phi plus and phi minus are the guys that are swollen by the W's. Let me find a Higgs to W coupling. Should be down here somewhere. So that's the part I didn't explicitly. Here. See one here, Higgs W, and the longitudinal component of the Z. It's with the one of the 2 weak couplings. But you have all kinds of interactions, right? This is Higgs, again, with a W. It's G2, but sometimes it's different, right? This is G over the cosine of theta, is Higgs with the Z. So they are very complicated. But it's just algebra, right? There's nothing more than some very big distribution of multiplications to do, right? There's no tricks here. It's just you just substitute the Higgs there and do all the products. You get this huge thing that comes all the way to this red line in the bottom here. This is just interactions between the Higgs, the W's, and the Z's, and the photon, right? The first part there, number 1, is QCD. So little g is the gluon, and big G is the ghost, the Faddeev-Popov ghost for the gluon. That one we didn't talk about because we didn't talk about quantization of non-abelian gauge theories, right? But don't worry about it. It's just a ghost. It goes away eventually, right? But that's the whole thing. Well, it's the one I wrote before doing the distributive, right? This one. Where is my slide? Here. That's the way you see it written in shirts everywhere, right? Let me see. That one. Right? This is the covariant derivative. It has all the powers of W's and Z's. This is the full Higgs doublet. If you don't do the distributive, that's the compact form. That's what is in the ICTP, the Trieste ICTP shirt, right? You have this term over there. This is part 2. That's the compact way of writing it. Right? So it can be really compact. Right? So again, this is equal to that part 2 in the expanded Lagrangian. Okay? So, any other questions as far as the standard model goes? Most of them, right? Because most of those interactions involve W's and Z's, right? And those were studied extensively in the lab, the predecessor of the LHC, right? Which did electron, was a leptonic collider, and choose energies very carefully. So you produce Z's like crazy, right? And look at the decays of the Z's and the W's. And a lot of, still a lot of the most precise measurements we have for the standard model come from that accelerator. But you see, even if you look again at that mass, there is a trend you can see, which is quite clear, is that the constants in front of these operators are always the same, right? It's the cosine of that. This is the cosine of that weak angle. Again, the cosine, G, sometimes G prime, the mass of the guys, right? So there's a huge number of operators, but there's not that many free parameters, right? That's why people say the standard model is so successful, right? You have all of these are different scatterings. They are in principle, right? In practice, it's not always that easy, but in principle, they could be measured independently, each of these operators, right? And still, you have very few parameters that should fit all of it, right? And that's why it's amazing that it works. Yeah. Many, in fact, right? For instance, just to give an example, suppose we didn't have the Higgs, right? Would still have the quark condensate from QCD. So there's one thing in QCD, which is the Q bar Q vacuum expectation value is not 0. This is very important for QCD. It's responsible for chiral symmetry breaking, generates the mass of the pions. There's a lot of consequences of that. But that thing also, it's a scalar quantity, could couple to fermions and would give masses to the fermions. But they would be of the scale of QCD, GeV scale, right? And now your universe would be very different. So a lot of people, before the discovery of the Higgs, right, a lot of people proposed mechanisms like that. If you had a fourth generation of fermions, for instance, that could give mass to the Higgs. You could have more complicated scenarios, or instead of having just one scalar, you have many, right? But in all of these, you have to be careful to not violate what's already measured, right? So putting more scalars has to be done very carefully to avoid, for instance, ruining the rho parameter. But there are many models, right? Beyond standard model physics is very rich. Right? So now, if I go a little bit forward and finally get, just so you don't say you were fooled by the title of the course, I finally get to open problems in the standard model, right? In one slide, right? And there are different kinds of problems, right? There are problems that are really experimental problems, right? Effects we have measured in nature and the standard model does not explain. There are problems which are theoretical problems, which are things that are in the standard model but do not make us happy, right? It works, but you know, it's not beautiful. And you have all these kinds of problems. So this first one, the fermion masses, is more of the theoretical kind of problem, right? As I told you, all the masses of the fermions in the standard model will come with this interaction with the Higgs, but the Yukawa couplings vary a lot, right? The Yukawa coupling of the top is 1, for the electron is 10 to the minus 5. I already told you if I want to include the neutrinos is 10 to the minus 12, right? And we don't understand that. That is closely linked to the fact that we also don't understand why we have 3 generations, not more, not less, right? Why these things repeat, right? The properties in each of these generations are exactly the same as the ones before, with the exception of the mass that gets heavier, right? That's the kind of thing that happened to the periodic table and made us suspect that something was behind it, right? And it's happening in the standard model. It could be that nature just decided to be like that, right? These couplings could just be these numbers that were set through a selection of multiverses, if you want, to stop doing science at some point. But, you know, numbers, right? Or there could be reason behind it. It kind of stinks of something is going on. But that's theoretical. The two next ones, right? Well, within this problem, there's the neutrino mass problem, and that is this experimental, right? Neutrinos have masses, and we don't know if they have masses through the same mechanism the other ones have, or it's something more complicated. There are other solutions, like Majorana masses, seesaw models, you name it. There's a lot of solutions. And we have just no data to know which one is going on, right? Dark matter is another experimental problem, right? It's very hard to explain dark matter with modified gravity. Nowadays, people that still do modified gravity do it for a fraction of all the standard dark matter, not the whole of it, right? Because there are some effects like bullet clusters and things like that which would demand an isotropic gravity of some sort, which is ugly as hell, right? So it's not easy, and of course, in the standard model, there's no candidate for dark matter, right? This one is also, you could call experimental, right? We are made of matter. You don't see antimatter anywhere, and we don't understand why there is more matter than antimatter in the universe, right? So there's this guy, Sakharov, that proposed 3 conditions that you would need to satisfy to generate this asymmetry, right? It's called baryogenesis, it's the matter-antimatter asymmetry, and it demands CP violation, strong phase transitions, in some way to violate baryonic number, right? And 2 of these conditions are already not satisfied by the standard model. There is a non-perturbative effect in QCD that allows you to violate, it's called Phaleron, the baryonic number, but CP, the amount of CP violation that you have in the standard model is not big enough, right? And also the phase transition is a crossover in the standard model, and it should be first order, or at least second order phase transition to generate out of equilibrium effects. And finally, these are very theoretical problems, which are fine-tunings in the standard model, right? This is hard to discuss with you because we didn't go through loop effects in quantum field theory. But the fact is that loop effects will change those numbers that we are reading from the Lagrangian. Sometimes they change those numbers a little, sometimes they change those numbers a lot, right? And some numbers which are not protected by any symmetry of the model, those change a lot. And one of them is the mass of the Higgs. So if you believe that the standard model is valid up to very high scales, I don't know, grand unification scale, 10 to the 15 GeV or the Planck scale, right? Then the mass of the Higgs should be around there. In fact, all scalars that we have ever seen in nature are quite close to the cutoff of their theories, right? The Higgs would be the first and only fundamental scalar, for one, and also the only that is living far away from the cutoff, right? We know no other example, right? And also there's the cosmological constant. I show it appears when you have these condensates, right? You calculate cosmological constant from quantum field theory, from the standard model. You get a number that is 10 to the 120 bigger than it should be, right? A little bigger. And of course, these all can be, all these problems can be solved by just putting an effective operator at the UV completion of your theory. But then you are assuming a cancellation between the infrared physics and the UV physics, which is something which is odd, right? Usually, for everything we know in physics to this day, there is usually a separation of scales, right? You can do physics at a certain scale, only worrying about effects that are happening at that scale, right? So these are called the scale hierarchies or fine-tunings because that's what you're doing. You're tuning some theory that happens at very high energies against one that is happening at low energies. Right? Again, it could be just the numbers came out that way on the multiple universe roulette, but that's not a very predictive theory, and there are many beyond standard model models that attack that problem, right? Sadly, this is the one that predicted that this first one, right? That you should have new physics at the LHC. So that's the main argument against it, right? We are seeing nothing to this moment. Right? Now I just want to focus a little bit more on this one because I want to be very tendentious and give you my point of view. Right? And the one I like is this plot. This is all the parameters for the standard model. Right? This is how many parameters there are. Of course, you could choose to have the Yukawas. You could choose electric charge instead of G and G prime. Right? So this is one of the many bases you could choose. This is chosen based on what is more precisely measured in experiments. Right? It's not chosen by theoreticians. But the thing is, of all these parameters, there are 19 there. Only these 3 and this one are not related to the Higgs. Right? Out of 19, there's 4. There are just the gauge, the 3-gauge couplings, right? And this one, which should be 0, right? It's related to another fine-tuning problem, the strong CP problem. But the rest is all Higgs physics, right? These are basically, all these in red now are basically equivalent to choosing Yukawa couplings, right? All of those. It's just a different basis. You see the masses there. These are mixings because eventually you have to diagonalize the mass matrix. This is a complex phase that is left over once you absorb all phases that you can absorb, right? So most of the standard model is related to parameters of the couplings of the Higgs, specifically the Yukawas, right? These last 2 are related to the potential of the Higgs, right? This is the quadratic part of the potential, and this is set by the quartic part of the potential. But all of the others are Yukawa couplings. And if I include the neutrino as a Dirac fermion, you get extra 7, right? You have 7 more parameters, right? 3 masses for the 3 neutrinos, 3 rotations, and 1 complex phase. So another 7 parameters, just Yukawa couplings, right? And that's very odd because everything but the Higgs in the standard model couples according to these gauge couplings, which are universal for the model. The Higgs couples differently to every other particle in the model, right? To each particle, it has a different coupling. Where have you seen that before, right? We know a few cases where that happens, right? If you look at atomic physics and you look how a carbon couples to a carbon and oxygen couples to a carbon, very different interactions. Why? Because these are complex, structured objects, right? Same goes for the pion, right? The pion couples with the proton one way, the neutron another way. You have these complicated form factors in QCD that, because these mesons and hadrons are made of quarks. There are complicated structures inside. So the coupling is not universal because it depends on the configurations, right? So these reeks of composite states, right? Especially the Higgs, right? It smells. I mean, it could all be just numbers chosen at random by nature, right? It is what it is, and the Lagrangian works. But it kind of smells of that the Higgs is not really fundamental. It has some hidden structure inside, right? And that's my preferred extension of the standard model. There are many people that don't like this. Right? Also, I come from QCD, so I'm biased in that way. Right? But that's, I think, the last thing I wanted to say. That's all. Thank you for the attention.
Very good. We have time for questions.
Does 2 doublets models of rigs has something to do with this internal X structure, or is another thing?
No, it's another thing. Right? So you could put a number of extra scalars in the theory that includes a second doublet, right? A third one, a fourth one, right? There are specific ways you can put those guys that do not change the rho parameter, right? The main motivation for 2 Higgs doublet model is that it is needed for supersymmetry. So if you believe that at some higher scale you restore SUSY, you have supersymmetry, you need 2 scalars. Just one won't do because you match the scalar with a fermion, the fermion that has more degrees of freedom. So you have to start with 2 doublets to get the fermionic Higgs, right?
All right.
the partner, the supersymmetric partner. But it doesn't solve some of these problems. One of the problems it does help, it introduces more CP violation. So it might solve the lack of enough CP to generate baryogenesis. I don't know about the phase transition, to be honest. Maybe with an extra hit, the phase transition becomes steeper, but that I don't know. There's one.
Yeah. You said earlier in the lecture about that you wanted the states to be, you want the particles to be eigenstates of interaction. Can you explain a little bit more?
Yeah, that is what I did a few slides later, right? So the W's and the Z's, that redefinition of the W's and the Z's were made so that the interactions look like this one. Let me go back, like this. Right? So this is the guy that actually interacts with the fermion, that gives you the covariant derivative. Right? So that interacts like a positive W, a negative W, a photon, and a neutral Z. Any other basis that I choose would be more complicated. Right? Like I would have a W that has no definite charge. So every interaction you would have to sum over various interactions to see that charge is conserved. Right? So when I do this choice of fields, I am in the basis of interactions, right? I produce this state through the interaction instead of a combination.
Thank you very much.
Well, here. It's not.
Does the standard model up to this day say anything at all about dark matter? Does it have any model or something for the dark matter?
Not the standard model, right? So the thing about dark matter is that it has some properties which must be satisfied, right? It shouldn't have electric interactions, right? It does not emit or absorb light, right? Not strong interaction, right? And then there is a non-trivial condition, is it shouldn't be too light. And that comes from cosmological models, right? At the time of structure formation, if dark matter that was around was relativistic, it would wash out structure formation, and you wouldn't have as many galaxies as you have, right? And that excludes everyone, right? Not having charge excludes most, but the W, the Z, the photon, the Z, and the neutrinos, right? That's the only particles that have no charge. But the W's, the Z decays really quickly. The photon is massless, right? And the neutrinos are too light. Also, I forgot to say, right? Dark matter should be long-lived because it's around since the creation, right? So there is no candidate for dark matter in the standard model that is consistent with the lambda CDM model. That is the standard model of cosmology. Right? Lambda means cosmological constant, and CDM means cold dark matter. Cold is non-relativistic. So it need to be heavy so that in structure formation times, it was moving slowly. It was cold, or at least warm, so there's some space there. But neutrinos are just too light. So there's no particle in the standard model that can be dark matter.
Right. And something else, just to see if I got it clear, the thing when you mentioned how almost all of the parameters of the standard model were reduced to, I think, 5 because of the Higgs mechanism, that we will say it's more like a problem because it doesn't sound good, right? That all of a sudden, because of the Higgs mechanism, we have a huge reduction of parameters. Am I right?
Well, the Higgs mechanism, that depends on the way you look at it, right? So when I talk about a reduction of parameters, I'm saying that the specific pattern of symmetry breaking is very predictive, right? Generates lots of operators, but they are all related. That's because the symmetry is not really broken, Right? This name is very bad. It's the historical name, but the symmetry is just hidden in a non-trivial way in the Lagrangian. So all these operators are related to these constants, right? And that's what I have been calling a reduction of parameters, right? Now, saying introducing the Higgs reduces parameters, no, right? If you take SU2, U1, and SU3 seriously, and that's just it, everyone should be massless. Right? The fact is, it's not, right? So you have to introduce the Higgs to give masses to everyone, and then you get these all these extra parameters, right? To be able to fit all the masses and mixtures, right? So you see, all of those are related to Yukawa couplings. Right? These two are the potential of the Higgs, and these four are the only ones that are really more intrinsic to the symmetry. Right?
Yeah. So you said that in standard model we ignore gravity. So, but dark matter only interacts with gravity. So how we could?
Yeah, the thing is, the only way we see dark matter is gravitationally, right? That doesn't mean it's the only interaction it has. If that's the case, we're screwed. We'll never know much about dark matter, right? Suppose it's just gravitationally interacting, no other interaction, we won't know what it is anytime soon, right? Because that's even weaker than 10 to the minus 12 that I said for the neutrinos, right? The thing is, you have to make assumptions, right, to attack the dark matter problem. And the assumption that is behind my affirmation that dark matter is not in the standard model is that dark matter is made of particles. Right? If it is made of particles, it should be here. Right? Then the decision is what particle it is. If it's not made of particles, then I'm not amazed it's not here. Right? And there are options for that. Right? So they are usually very constrained. So I'll show one. I have one slide here that can give you just one alternate scenario, just to say I'm not completely biased. Let me find it. Just a sec. That one, right here. This one. So this is what is called a macho. Right? It's a massive, compact halo object. So it's something which is produced by astronomical processes, right? Some very small white dwarfs, I don't know, primordial black holes, so big objects made of protons and neutrons, but they are so small that you don't see them because they just do not absorb enough light. But they are there, and you have a dust of these guys around, and we're putting constraints to that. So this is the ratio of dark matter that could be machos, right? So one here is all the dark matter is machos. This is just a small fraction of dark matter is machos. And all these color are experiments that are excluding machos, right? But there is one point here, you see? There's one point there that is not excluded. So if you had around sufficient numbers that the mass of the primordial black hole, in this case is a paper for primordial black holes being these machos, right? If they had exactly this mass here, maybe dark matter is just a bunch of black holes really spaced out, and you don't see them, not because they do not absorb light, it's just the number density is really small, right? It's an option, it's there. Then it shouldn't be in the standard model, or it is already, because black holes are made of protons and electrons, right? So that's an option, right?
And I have another question is about the possibility of new particles. You think there may be more, or is it just
well, it's always a possibility, right? So what we know from, I don't know, history, right, is that if you go from the size of the observable universe down to the electroweak scale, you do not change like 3 orders of magnitude in the scales you're looking at without having new objects, right? You basically go from galaxies, clusters of galaxies, star systems. And every level you need new degrees of freedom to describe what you're looking at. You cannot go more than 3 orders of magnitude without changing everything, right? Now, to assume there's no new particles up to the Planck scale, you would have to have like a desert of 15 orders, 18 orders of magnitude now, with no new things. Again, it is a logical possibility, but you cannot tell that. That is, again, in the nature of quantum field theories, right? If you are away from the cutoff of your theory, which is the place where new stuff shows up, you move away from that, right? Your normalization group equations tell you that all the effects that happen there go to zero really quickly. So everything looks fundamental until it isn't, right? You only see things deviating from the fundamental behavior when you get really close to this cutoff, not far away from it, unless there's some very special condition, right? So the fact that it is working right now does not tell us anything about if these fields are really fundamental, or they are made up of more stuff, or there are new particles. If they are heavy enough, you don't see them, right? You don't have the energy to see them, and you don't have the precision to see the effects in loops, right? So in either way, you don't notice them unless you go close, right? Then you can say, is there a motivation, right? So now that's the flip side, right? The flip side is, we had an indication for the scale in which we built the LHC, right? Two, actually. One, that the Higgs couldn't be heavier than 1 TeV without violating unitarity. That's a strong one, right? And we built the accelerator there, and we found the Higgs. If the Higgs was not there, something else should be to restore unitarity, right? Probabilities should add up to 100%. Otherwise, things will get real nuts, right? But aside from that, we also had this hierarchy problem that told us, even with a Higgs of 100 GeV, there should be more. That didn't show up, right? Now, if you want to go forward in energy, build bigger and bigger accelerators and get more and more money from politicians, right? Things get harder now, because now all these problems can be solved at any scale. If you throw away the hierarchy problems, you could have a solution for dark matter at 1 TeV, 100 TeV, or 100,000 TeV. Nobody knows, right? That depends on the coupling of dark matter. Could be much weaker than the weak scale, for instance. Even if it has other couplings beyond the gravitational one, could be really weak couplings, right? So it becomes the kind of science that is more exploratory, right? You have to convince people that, oh, I want to build higher or more precise particle physics experiments just to keep looking, because who knows? Maybe we find out that the electron is composite. Huh? But that's a weaker argument. It's harder, because you could build an even bigger accelerator and find nothing, right? But again, that's I compare that a lot with space exploration, right? It's the kind of really exploratory science, right? And in terms of money, to be realistic, we spend much more money just killing each other, you know. So maybe one day we can convince people to deviate a little bit of that money to exploratory science. But it has become hard in the sense that now it's hard to make a point that if you build the FCC at 100 TeV, you could find something, but you could not find it. And that's a hard sell. Me. Okay, I have the microphone. Yeah, he's asking if there's a sense in which you could talk about a dark standard model. Well, I can make a sense right now. I don't know what you have in mind, right? There's a lot of dark matter models that essentially you postulate some other matter that has none of these interactions, right? And since it does not interact at all with the standard model, it's a dark sector. And then you put one interaction that connects these two separate sectors just to be able to explain how both were produced in the same Big Bang, for instance, right? And that is called Higgs portal model. So there's Higgs portal, where only the Higgs speaks to both of them. There's gauge portals. There's many different models, right? And then you have dark photons, dark Z's, dark everything. You can be a complete copy of the standard model, right? The sky's the limit. The problem is that there's one thing to keep in mind, right? There's I don't know, hundreds of beyond the standard models, right? Some solve one of these problems, some solve 10 of them, right? But of course, if you give me enough parameters, you know the saying, right? So as models get more complicated, they fit everything, they solve everything. Everything is solvable with enough parameters, right? But at some point, you have this give and take where you stop believing models because they become too convoluted, right? Who knows? The standard model is quite convoluted. That may be something you agree with me at this point, right? There's a lot of parameters here, right? There's 19, and, but it's the smallest one that works. Right? These Zakharov conditions, they need basically three things to happen, right? You have to violate CP and baryonic number, and those two together is just that you are producing baryons and antibaryons with a different probability, right? But that does not help you at all if you are in thermal equilibrium, because the matter and the antimatter have the same mass. So even if the probability in one direction is bigger than the probability in the other direction, it will balance out by thermodynamics, right? So you have the same number of baryons and antibaryons. So you have to have, at some point in the universe, these transitions that produce more baryons than antibaryons happening out of equilibrium. So if you imagine a first-order phase transition, the phase transition I'm referring to is when the symmetry is broken, right? If you put these theories in finite temperature, these parameters for the Higgs potential, they become temperature dependent, right? So I wrote this potential in this way, right? I'll just simplify. Right? It's essentially this. So a downward part, and then it restores, you get the Mexican head. If these are temperature dependent, and this one is temperature dependent, you could have a potential that when you heat up the universe, right? The potential that started like this goes like this and then becomes this as this number becomes positive, right? That actually is the way it works in the standard model. And so as the universe cools down, at some point you have a phase transition from this potential to that one, right? You start with a vacuum here, and eventually you are in a stable vacuum that needs to. And that could be first order, like form bubbles, right? Like ice or water boiling, right? So you form these bubbles, and on the walls of the bubbles, as they expand, you are out of equilibrium. So you need some out of equilibrium transition for this electroweak phase transition in order to have a region in the universe where you're producing more baryonic matter than anti-baryonic matter and not washing it out by thermal equilibrium. And the standard model does not do that, right? You need at some point to have like a bump here so that you have a first order. Right? In the standard model, as we know it, is completely smooth. It's a crossover, so there's no bubbles. And that's a problem because it's one of the conditions, that is one of the ways that we know to produce baryonic matter, right? So you could put some extra particles in the model to make this transition stronger. There are models that deal with that.
One question there?
Is there a prediction to why the hypercharges are small ratio of small numbers?
Well, the hypercharge is chosen to give the right charges, right? And there is this lack of monopole argument for integer charges, right? So then it's a consequence of that, right? I'm in the wrong set of transparencies, but it's essentially the hypercharges are chosen to give the right charges, and then there are arguments for the charges.
Yeah, so I know that people are looking for gravitational wave interaction with dark matter, but I was wondering, how is it theorized that, you know, like dark matter interacts with gravitational waves, or maybe the sources that generate the gravitational waves?
I think, well, now we're going outside my field of expertise, but I think it's really simple. In terms of how it interacts with gravity, all you have to care about is that dark matter has mass, right? And you have to know roughly the mass density, the distribution of mass, right? If you know that, you'll be able to make all kinds of predictions on how it interacts with gravity without knowing any detail, if it's a spin 1, spin half, or scalar, whatever it is. As long as you know the mass density, right, at least the interaction with the usual gravity, right, the Einstein gravity should be set, so you don't depend on details. As far as I know, I don't know if anyone has any comment on that, but I think that's all. You don't have to know what it is, right? It could be black holes or particles, it's the same, as long as you know the density.
Okay, so if not, let's thank Ricardo.